All right. Thank you, Fantina. I hope everyone is hearing my voice well. So yes, so the tour of the Quonops tool is going to happen this afternoon, and this morning the plan is to give some background information on modeling, on how modeling is done, why modeling the sound is important, so that you have the background to then have all the keys to understand and to interpret and interpret the noise maps. I will show a number of examples based on other projects and previous projects we participated to. And the day is going to be, so there is a 2-hour session this morning, and then a 2-hour session this afternoon. So we'll see if we will need the 4 hours, but maybe yes. Especially, I think it would be good if you can ask questions. I have divided the day in 6 items, and maybe you can we can stop after each item, so that to have some time to for you to ask questions. I think that would be probably the best. So the idea here is just to recall to talk a little bit about underwater sound propagation and the effect of the environment on the propagation. Then the concept of noise mapping. What is a noise map? How it is built? And what does it show? And how to read a noise map. Then something more technical here on the calibration of the noise map, which is how we use measurements to calibrate the maps, to ground truth the maps. And then 2 kind of cases, maybe, on how to use the noise map for regional management. That's based on what has been done in the BIAS project. Give an overview of what has been done and how it has been used. And another test case, which is the use of noise maps to assess the effect of sounds on marine life. And this is a work we've done on seals that I think is interesting. All that discussion I will present is very much linked to the discussions we currently have at the technical group noise of the EU. That is supposed to provide methodological recommendations to the member states on setting thresholds for the good environmental status, especially for descriptor 11 on noise. So it's very much aligned to the discussion and what is going to be proposed. And then at the end, a demonstration of the interface itself, a tour. All right. So let's start with sound propagation. So just and let's start away with some maps. So this is the idea here is to illustrate how viable can be the sound propagation. 2 examples. On the left, you have 2 plots, two maps of the same source, the same sound source, at the same frequency, the same day, but at 2 different places. And you can see that the way the sound, so here it is offshore Pisa, Livorno. Okay, outside Livorno, here you have 1 sound source. And the sound around the source, so first comment, is not distributed homogeneously around the source, because you can have the coast, obviously, but also because you can have some bathymetric features, for example, that will change the propagation according to the azimuth around the sound source. And if you take exactly the same source, the same day, at the same time, somewhere else, which is, where is this? In the south of Italy, I think. You can see that because the conditions are very, very different, the propagation is very, very different. On the right, again, two maps here, same source, same frequency, same place, but 2 different days. One is in winter, the other one is in summer. And you can see that the same source will have very different, although you inject in the environment the same amount of energy at the source, the propagation is going to be very different, and the distribution of the sound around the source is going to be very different. And that's because the only thing that has changed here is the oceanography, the temperature and the salinity. Okay, so propagation is a key element when dealing with underwater sound. This is more or less the same illustration. I hope your screen is refreshing sufficiently fast so that you should be able to see 3 different situations. It's a single vessel at 3 different positions. One is in the Atlantic on the west. In the middle, it's the Gibraltar Strait, and on the right, it's the Med, the Mediterranean. It's the same vessel, more or less at the same time. And you can see that the distribution of the sound around the vessel is very different according to where the vessel is located. So the only thing that the source level is the same, so the energy introduced in the environment is the same for each location. The only thing that changed is the position. And you can see that in the Atlantic, we have an environment that is fairly deep water with some bathymetry on the north, steep bathymetry on the north, but it's mainly deep waters. And with a temperature and salinity that is representative to the Atlantic. In the middle, it's shallow water. And on the east part, this is the Med, where you have a very different distribution of salinity and deep water as well. You can see that although in the Med and the Atlantic, you are in deep waters, because the salinity distribution is different, you have a very different pattern around the source. Maybe I should have stopped. Oops. Okay. All right. Okay. Here you have something interesting. You can probably see here these 2, in French we call that résurgence. So in English, I don't know. You can see that, okay, the sound level when you go out from the source level is decreasing regularly, okay, which makes sense because absorption and because the sound spreads, so the energy is decreasing. But at some point, the energy here increases again in this area. And that's because you have some reflection. The sound is reflected on the bottom, which is quite deep, and then goes up again. And so that it adds energy here at this location when you have the sound that is traveling more close to the surface, cross the sound that is going down and up again, and close to the surface again. And that creates this kind of area here where you can have more energy than closer to the source. Okay, so the modeling, when we do modeling, actually what do we do is to solve an equation. I'm not going to enter into detail on that equation. It's called the Helmholtz equation. And this is the description of the pressure field in the water. All right. And modeling exercise is solving these equations for a given environment. And the sound, because of these equations and because of the oceanography and because of the bottom topography or the bottom type, bottom properties, the sound is not going to travel in straight lines in most of cases. Sometimes it does, but most often it does not. And here on the left, you have the sound speed profile. So the sound speed profile in the water is derived from temperature and salinity. And what is happening is that you can have a mixed layer. So, it's a place where salinity is constant and temperature is constant. That happens when in summer, for example, when the temperature close to the surface is increasing, and because of the wind and all that, we call that a mixed layer where temperature and salinity are quite homogeneous. You can have, if you put some sound in this layer, the sound is going to travel close to the surface, like this here. All right. Then below that mixed layer, you can have a thermocline, which is so that the sun has heated the ocean on the surface, but not on the deep, not deeper, not that deep at large depths, right, where the temperature is going to remain very stable and very low at maybe 10 degrees or something like that. So you have an area where the temperature is decreasing from the temperature that is on the surface, heated by the sun, to the temperature, the constant temperature in deep waters. It's called a thermocline here. And this gradient is going to change the curvature of the rays of the sound, okay? So that some of the sound will be refracted on top of the thermocline and go deep and then go up again toward the surface. And some of them are going to go deep and then go even deeper, okay? Until it reaches the bottom and then rise again toward the surface. In deep waters, what is happening is that the temperature is fairly constant, and but the pressure, the static pressure, is increasing because of depth, and that creates this gradient, so that you can also have some other rays that will be refracted towards the surface in deep waters as well. So it can be very complex because you can have all this situation. According to the sound speed profile and to the oceanography, it can be very, very complex. But the good news is that this equation is describing all these phenomena. So there are now how to solve these equations. So there are many ways to solve these equations. It can't be solved right away. You need to do some assumptions to simplify it. And that's why we have different types of models. In Quonops, we do use two types of models. The one is a ray tracing, and the other one is a parabolic approximation, which are probably the most used modeling technique in the world, I guess. The good thing is that both models, they solve this equation with different assumptions, but both of them are taking into account the conditions, the oceanographic conditions in the water column, so the sound speed profile, and also the bottom type. So it's quite a fair estimation of the propagation, and it will describe all these phenomena that I just described here in the previous slide. There are some other ways of doing modeling. Other models exist based on different assumptions. So the ray theory I talked about, you have normal and coupled modes. parametric equation, a talk fast field, and actually there is quite a diversity of way of solving the equation. But each of them, because of the assumption you need to take in order to simplify the equation, the models can be valid. They are valid for some. They have some limitations. Usually, limitations can be divided into models that are suitable for shallow waters. So what we call shallow waters is below 100 meters of waters or so. And some other models are more suitable for deep waters. So when the water depth is exceeding 100 meters. And some models are more suitable for low frequency sound and some others for high frequency sound. Here, the frontier between low frequency and high frequency in this table has been set at 500 hertz. I would say 500 to 1 kilohertz is probably the frontier. And then another thing is that some models will be able to deal with range independent environment, so that it means that the environment has to be constant versus range. Like a constant bathymetry, for example, and a constant temperature and constant salinity. And some others, they deal with range-dependent environment where the bathymetry can change, where the seafloor, the nature of the seafloor can change, and the temperature and salinity can change versus the distance from the source. So, and here you can see what model here and what type of model is suitable in what conditions. All right, so you can see that. So we use ray theory and parabolic equation, and actually we use parabolic equation in the low frequency bands, which is suitable for shallow water and deep waters. And we use ray theory in the high frequency, so we use it above 1 kilohertz and sometimes 2 kilohertz, depends on if it's shallow or deep waters. But basically, we use ray theory at high frequencies in shallow water and deep waters. And both are range dependent, so we can really describe the environment with a change bathymetry and really a change as well, the distribution in temperature and salinity in the ocean. All right, so maybe any question at this stage? So that was just a kind of introduction on modeling the propagation. Just to warm up. Are you still there?
Yes.
Okay.
Yes. Yeah.
Thank you.
Is there a question at this stage? I don't know.
No, I guess there are very many different ways of modeling, as you said, but you see that what you have used, so the one that you selected is tested. I mean, it works well. So I guess.
Yeah. Yes, exactly. They work well. They work well in kind of all conditions, both together, and they've been validated quite a lot because they are very widely used. So that was very important when we selected the models to use.
Okay, but I have a question. Are you still so you have your well-established model that is tested and so on and so forth, but are you still developing it? So are you still modifying the code and seeing the latest development and of the research on this field?
Not
for example, I think of, for example, of the fields generated by the how you model the fields generated by ships. That I think was something that Mario Felli pointed out, that maybe there could be developments on that, like based also on experiments and things like that.
Yes. So the modeling of the propagation, we don't develop that at this point. the only change we've done is more linked to increase the speed of the calculation using a distributed architecture. But from the physical point of view, we didn't change anything in the code because we wanted to have a validated code. It's quite difficult actually to validate a code, a model, because you need to really control all the parameters. So it's a very heavy work. So we decided not to change anything on the code because it was already validated by a number of different organizations. Then this is for the propagation. Then what you mentioned is for the source. Here, this is a quite opposite situation. The source model, this is something quite new, and especially because you have a very large diversity of sound sources in the ocean. And there is, this is quite an active field on how to improve the modeling of the source itself. And that's something we are working on.
Okay, thank you. I think that Mikkel had a question for you.
Yes.
Yeah.
So Thomas, what about the interaction between sources? So if I put the two ships, for example, in the model, the noise level are added, or there is an explicitly interaction between the two noise field?
Yes. So both the noise fields will interact. They will interact coherently. Okay, this is a very difficult word, probably. How can I explain? I don't know how to explain that simply. So they will sum up, but in some places they will, because this is all vibrations, all right? The sound is a vibration. So when the two fields, they are both they make that the water elements are vibrating, and in some places the vibration will be in phase, so that they will really add up. And in some other places, they will be in opposite phase, so they will just destroy themselves, and the field will be zero. And of course, you have all the combinations in between. So they will really interact, both of them, and so that and sometimes sum up, sometimes not sum up.
Okay.
So we do the modeling, we do that for each source individually, and then we sum the different fields to get the total field.
Okay. And I have another.
Yep.
Another question is when it's like the Doppler effect. When I am traveling more or less fast, then the frequency changes because of the movement.
Yes.
Also, in underwater noise, it's happened, and you can simulate this.
So yes, it happens. Now, usually the sound sources in the ocean are quite slow, actually.
Okay.
So the change in frequency is not really significant. Much less than much less than all the other effects I talked about. It's the same for the current. The current could introduce some Doppler, but you know, the current is also very slow. Well, when you are at sea and deploying an instrument, it's not, you don't feel it's slow because it's strong, but it's not very rapid, right? The current is about a few knots maximum, which is not much. So the influence on the frequency is very low. The Doppler effect is relative to the speed of the sound and the contrast you have. So the speed of the vessel compared to the speed of the sound in the water, which is 1,500 meters per second. So the contrast is very high, so the Doppler is very small.
Okay.
Same for the current.
Okay, thank you.
All right. Let's continue then. Underwater noise mapping. So now we know how to model the sound.
Thomas, it's Predrag.
Yes.
Yeah,
Hello.
can I interrupt you? I didn't know whether your first theme is over or not, and now I see that you are moving on. I would like to ask you a few comments on the propagation of a sound in a shallow water. What we are doing in this project, we are working in the area of shallow water. Most of the northern Adriatic is below 50 meters, and we have 3 measurement sites in the depth of less than 20 meters. So, just a few comments to add to the other propagation in a shallow water versus frequency versus cutoff frequency, and few words about that. I think it will be very useful for us.
Okay, very well. So the shallower the water, the more intense is the interaction between the sound and the bottom. All right. So the challenge in shallow water is that you have the description of the bottom will have a very, very important role to play. Okay, so that's the first thing. The second thing is that too shallow water, the models doesn't really work. So, for example, we don't really like to go below 5 meters water, then we don't trust the results anymore, really. It becomes very challenging. So that's the second point. The third one is about the cutoff frequency. So yes, in order for the sound to propagate in the water column, it kind of needs to have space to travel. Okay, so if and when I say that, I mean that the wavelengths. So the wavelengths, is that clear for everyone what the wavelength is? The wavelength is the okay. The lower the frequency, the higher is the wavelengths. Okay. The wavelengths. So the water depth needs to be larger than twice the wavelengths. All right. If not, the sound cannot really propagate in the channel. If you want an image, it's because there is not enough space to enter the tube in some way. So it means that if it's very shallow, then you start to have some frequencies where the sound just do not propagate. It will propagate for a few meters, a few tens of meters, but then it will vanish because it can't propagate very far. That's called the frequency when that starts, or the frequency below which the sound does not propagate very well, is called the cutoff frequency. So when you measure the sound from a source, if you are in a very shallow water, for example, if you are, okay, this is by memory, but roughly to give some order of magnitude, if the water depth is about 40 or 50 meters, I think frequency is 50 hertz, more or less. Forgive me if this is not very precise, but it means that if you measure a sound source in 50 meters of waters, the results you'll get, you will have very low levels below 50 hertz. And the sound that is really propagating in the medium you will be able to measure that above 50 Hertz. This is why when you do a measurement of a vessel noise, it is required to be as much as possible in deep waters. And measuring and assessing the source level of a vessel in shallow waters is much more challenging because of that phenomenon. Does that address your item, Predrag?
Yes, of course. Thank you. But I just thought that it is important because we are measuring in a shallow water, so that all other have that feeling of problems with low frequencies, large wavelengths in a shallow water. Then the very low frequency content of a whole spectrum is not let's say not valid under the cutoff frequency. Okay.
Right.
Yeah. Thank you.
Yeah. Very good. That's a very good point. Okay. Now let's talk about mapping. I have a first slide, which is a little bit the history of noise mapping. This is a very complex graph, but it's my friend Eric Baudin from Bureau Veritas who gave me that one. You can look at that afterwards, but the idea is to say that this topic here has really started to pick up when the MSFD has been published in 2010. Actually, there was a first project, Silent V, funded by the European Commission, that was already dealing with the sound, the noise from vessels. And we started to do our first maps in 2009. And it has really picked up during the Aqua project in 2012, 2015, where we really developed Quonops. That's where we have developed and validated the Quonops system platform. And the first really big use, at least at regional level, was for the Bias project in the North Sea. And now it's quite widely used in some other projects. And you can see that the number of projects, at least at the European projects, is increasing quite quickly. Regional projects, but also thematic project like Saturn that is going to start next year. Okay, so how does it work? The idea of noise mapping was to bring together all the information you need to describe the sound. So you need to know where the sound sources are located. For that, we do use the data from a number of maritime surveillance systems. Most of them are based on AES data, or you have another system which is called VMS, which is really used by fishing vessels, and they give you where your sound sources are located, when and where, the type of the vessel, the speed of the vessel, the length of the vessel, that will play a role in assessing how much noise they do introduce in the medium, in the marine environment. Then we need to describe the ocean, the water column, and the bathymetry and the sediment types. So we use here usually we use ocean databases, open sources, or for the Soundscape project we use the bathymetry and temperature salinity provided by CNR. And okay, this is for the temperature and salinity. And then we also need, of course, a ground truth at some point, which is all the different stations you have deployed. And from that, we have everything to describe the source and the propagation, and to calibrate the propagation based on measurement. So this is the principle on how it works. And when you do this, here is an example of a movie instant of the sound field at a given depth at 105 hertz. This is offshore Brest, where you have quite a large diversity of vessels. You have some ferries that goes from land to the islands here. You have some traffic here very offshore, which is the commercial traffic. And you have some coastal traffic that goes here along the coast, or that sometimes enters the Brest Bay, which is here. So you can see that it's very variable. It's variable because you have different time scale here. It's very variable because the vessels are moving all the time, as you can see. It's very variable because as the vessel is located at different places, the propagation is different at each places. And it can be also different variable because with season, the temperature salinity will change. So it changes slowly, but it does change. So at the scale of the season or even at a month, you can have changes due to temperature salinity change. So the mapping give a quite different view of the view you have when you measure. When you measure, if you put a hydrophone there, you're going to measure a time series at a fixed position that will look like this. Okay, and I've seen some measurements from the soundscape project, and it also looks like this, which is very different from a map. But it's very interesting to understand that each point of the map is derived from that. If you put a hydrophone, it looks like this. What you have is a superposition of two different things. You have a kind of background noise here, a background level here on the bottom. And close to this noise, you have some short events with higher energy, okay, that last maybe half an hour or so. Here is actually when a vessel is going to pass by the hydrophone, like now. It passed by a hydrophone, so it increases the sound close to the hydrophone for a short period of time, which is roughly about half an hour. Okay, so each time a vessel passes by the hydrophone, you have a peak here. And no vessel is around. You have lower levels. It can be either the contribution from all the different sources and with a long range propagation of the sources that are located far from the hydrophone, or it can be natural sound. For example, you can see that here we have an increase, a sudden increase here in this background level. And this lasts 1 day. And this is typically a windy event. So the wind has created underwater noise, natural noise, so that it has increased the background noise. Okay, but the noise from the vessels remains the same because that's not depending on the background noise. Okay, so it's very important to understand this kind of plot. Also, when you check your data, it's supposed, I mean, a long time series is looking like this all the time. Sometimes you have less peaks, sometimes you have more peaks, although here it's quite intensive. And you have this background that looks like this. The question now is, how can I represent this? Because this is quite very complex. How is that representative to noise? So some people said we should do an arithmetic mean. If you do an arithmetic mean of this data, you end up with this value here. So the question is that representative to my data set? Is the arithmetic mean representative to my data set? Personally, I don't think so, because, okay, this is the value, but it doesn't tell me about what is the maximum. It doesn't tell me anything about the background noise. It doesn't tell me not even something representative to the anthropogenic noise here, to all the peaks. A geometric mean would be here. A geometric mean means when you average the decibels, where the arithmetic mean means when you average the Pascal. Okay, it's very different because the decibels is a nonlinear scale. So when you do the averaging in Pascal and when you do the averaging in decibels, you don't have the same results. So if you do the geometric mean, you end up here. Okay, is that a better illustration? Is that a better description of my data set? I don't know. I don't think so. It doesn't describe much more than the arithmetic mean, the anthropogenic noise, nor the background noise. The minimum level is already actually, I think, more interesting because this is the minimum level. The maximum level actually is also interesting. At least you know what's the maximum that has been measured. I think the median is already more interesting because it tells you what is the noise level you had half of the time. And here it comes to the metric we have introduced, which is the percentile, which is actually where you quantify the level, you associate a level with a proportion of time where you have exceeded that level. I think I have, okay. So here you can select a proportion of time, so or a given level, let's say here 92 decibels, and you will count how much data points you have above this level. Okay, and compared to the total number of data points, it will give you a proportion of time. Here, for example, maybe 20% of my data points are above the line. It means that 20% of my time is above 92 decibels, which is already much more interesting and much more rich because using different values, different percentiles, you can have a very clear and simple description of your data set. It's also interesting because it directly describes how long a species is going to be exposed to a given level. And we all know that you can be exposed, that the duration of the exposure has an important role in when it's time to describe the effects, because you can be exposed to something very intense a very short time, or something less intense a long time, and have the same effect. So it's very important to understand that percentile, also because it's a very convenient way to represent the sound on maps. And every map that is going to be produced in the project are in percentiles. So it's always a level that's given by the color of the map for a certain amount of time during the period. And when you look at this, you can see that actually the most intense sounds are less frequent, and the low-level sounds are most frequent. And as you can see here, the sound that is here is linked to passages of the vessels. So this is only anthropogenic noise. So anthropogenic noise are usually most intense, but less frequent. While the bottom here of the noise is more related to natural noise in most cases, unless you have very, 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 very heavy traffic. But in most cases, this is related to the environment. So it's less intense, but most frequent, almost always there. So if you put that on a graph, you have the anthropogenic noise that if I draw a graph where here on the y-axis it's the loudness, okay, so low noise and high noise. The occurrence, less frequent to most frequent. What you will have, if you put your sound on that graph, you will have the natural sounds that are most frequent but less intense, and the human sounds are usually more intense but less frequent. In between, you have a gray area, or you have a superposition of both noises, a competition between both noises. here, which is a little bit more complicated to describe. What we do in the modeling, when we do the modeling of the map, we do model the natural noise. So not all sources of natural noise, but we do model the noise that is generated by the wind and the waves. And we do model the noise from humans, from the human activities, as long as we know the activity. And that's, of course, we need to know what activity is on, and sometimes we don't have a full description of that. But we have both components to produce what we call the total ambient noise, which has the both components. As you do when you measure, you measure both components. So just one word on how we do the modeling of the wind, the natural noise. Actually, we're just currently changing the way of doing this, but I think this is still an interesting approach. This is an example. It has been developed in the BIAF project. Here on the left, you have a video of the distribution of the surface waves versus time and space in the area. So you can see that sometimes you have some windy events and it will decrease and move. And we had access to the measurement here. It was 40 stations here across the Baltic Sea. And what we did is we compared what we call the background noise. So we compare that, excuse me, yeah. Okay, here. We compare that curve here, that level here on the bottom of my measurements. We compare that one to the estimation of the wave height in green. Okay, and you can see that you have a very nice correlation between both signals, both time series, and that's the proof for us that there is a direct relationship between the height of the waves and this level on the bottom of the level I do measure. Okay, so here in that case, we have a clear correlation, meaning that this bottom of what I measured is really generated by the waves. And if we plot one as a function of the other one, it gives a plot like this. And the bottom here of the scatter plot give us the relationship between the wave height and the level, the natural component of the noise. So now we know that at this location, if we have 4 meters of waves, it will generate 88 decibels at 125 hertz. Okay. Then, since we know the wind for all positions, we are able to convert this dataset into decibels and to add this to the anthropogenic noise. So we did that. So now just the results from BIAS, I think you've seen that 1,000 times, so I'm not going to spend too much time. So this is a small video. Each image is 1 month. It's 125 hertz. It's the 10th percentile. So this is the levels, 10% of the time. It's a monthly map. It means that it's 10% of my month. So this is the levels you reach at least you reach 3 days in your month. Okay, if I consider that 30 days per month. 10% of 30 days, that's 3 days. And that's the level you have. So the exposure during that month, marine life was exposed to those levels 3 days during the month, cumulatively. You can see that the map is made of 2 components. You have the shipping noise that is very stable from month to month because the traffic is always there. And in the background, you can see that the level is much more variable. And this is the natural noise, mainly. And you can actually, you have less, the level is quieter in summer when you have less wind and less waves, smaller waves, than in winter when it becomes all red in winter. And that's because in winter you have more wind and more waves. Okay. It's the same at another frequency, exactly the same result. So I'm not going to do that. So now the modeling, since we do have both components, in one hand I have the natural component, on the other hand I have the anthropogenic component, I can also look at how much the humans have added to the natural component, making the difference between the two. And that's the beauty of the modeling, is that we can map this and we can model that. And here's the example for 1 month in sorry, I don't know how to mask this, but okay. I think this is August. And so this is for 1 month, and that the excess level. So now we are, the decibel scale has changed. You know, it's not 70 to 140 decibels, which is the level you would measure. Here now it's a level that starts from 0 to a few tenths of decibels, because this is the level above the natural sound. Talk a little bit later on what is the use of that. It's a kind of measure of how much humans add to the environment. So here another example in the south of France. So here it's close Marseille, Fos Marseille. So Marseille is here. This is one harbor here, and you have another very large harbor here in Fos-sur-Mer. Okay, 2 harbors in the Med. And if we look at the different percentiles, so it's the same area, same period of time, same frequency. It's for 1 month. And if you change the percentile, you can see that the map is changing, because when you are at low percentile, so if you look 10% of the time, if you remember the other plot, the levels are higher 10% of the time. Back to that one. Okay, 10% of the time I will be somewhere there, right? So I will only measure the peaks. So my levels are going to be higher than the other percentile, the median level and the 75, which are going to be lower. All right. So this is exactly what you see here. Voila. So of the time you have higher levels, and you can see here the signature of the concentration of the ship traffic that travels here mainly, and then goes into the Fos-sur-Mer or Marseille harbor. You probably have another harbor somewhere here as well, actually. I should have checked, because here you also have a signature here of some traffic from there to there. And if you look at the median level, well, the signature of the Marseille harbor has disappeared, because Marseille harbor is has less traffic than the Fos-sur-Mer harbor. But half of the time, you still have anthropogenic noise here, just due to the traffic at the mouth of the Fos-sur-Mer harbor. You can even still see it a little bit 75% of the time, but with much lower levels. So this is how to read the maps, okay? And it's interesting to look at different percentiles. Usually we use the 10th percentile, which is a description of a really anthropogenic noise. 25% of the time, which sometimes helps to, this is fairly useful in area where you have less traffic. The median level, because it's the median, so it's half of the time, it's always interesting to look at this one. And the 75th percentile is also very interesting, because this is more representative to the natural noise. Apart from some places where you still may have a contribution of anthropogenic noise when you have some very heavy traffic. So what is the benefit of the modeling? It enhances the local measurement by giving a basin scale regional description of the area. So it's a very complementary view of what can be assessed by only measurement. Although modeling needs measurement to be calibrated, that's very important. It allows to understand geographically what is happening in the distribution of the noise, as I just illustrated with the harbors of Marseille and Fos. You can isolate several types of noise and origin of noise, as I illustrated, for example, with the natural noise on one side, the shipping noise on the other side, and then you can calculate the difference between the two to see the contribution of one noise above the other one. It can also be, if you have a construction, for example, somewhere, you could compare how much the construction work is going to add to the existing noise. Here you would put in one hand shipping and natural noise, and you will compare that to the noise from the project itself and look at the difference between the two. We call that a footprint, the project footprint. And you will be able to characterize how much the construction project is adding to the existing noise. It can also, because you have access to a map, that's very interesting to then identify and predict and interpret what is going to be the impact if you change the nature of the maritime activities, or if you change a shipping route, for example, or whatever special planning action you plan to do. And then also it's very useful to establish trends, since just one point is not necessarily representative of the full area, as we have seen. So to be able to consider an area and to work on an indicator on an area is much more relevant than working on an indicator that is just at a single point. Okay, I think I already said that. Yeah, okay. Footprint, I talked about that. So what we provide to the project is a statistical characterization of noise, because what we provide is a percentile map. Okay, we can provide maps at different frequencies. That's interesting if you have to address different species, of course, since the species can be sensitive to different frequencies. Okay, voila, that's the item about noise map. Is there any question?
Sorry, I have not a question, but just a curiosity. So about using percentiles, is okay to synthesize a series of data using box plot representation, for example?
Using what representation?
Box plot representation. I mean, with the median and the 25 and 75 percentiles.
Yeah, that's probably a good way to describe the data set. Yes.
Okay.
Yeah.
But it's better using the 90 percentile rather than 75. You say?
Well, I don't have a strong opinion of that. We look at 10, 25, 50, and 75. That's what we usually look at. We will provide to the project a bit more than that. We'll provide as well the 90%, and we provide 7 percentiles. Okay, so but from that, It depends a little bit on what you are looking for and what you're looking at, the property of the map. Sometimes 25% percentile is not very clear. It's better to use 10% if you want to characterize your anthropogenic noise.
Okay.
So it really depends. I don't have a strong opinion yet on that.
Okay. Okay.
Now that is because we were asking because now Antonio produced with the results of the processed data, for example, for the Acqua Alta station, we produced like a time series of the different frequencies. And so we were trying to represent the trend. For example, we can see that there is a trend of increase of noise with after the lockdown. So
Right.
we can observe that, and we can observe, for example, also in other stations, we can observe a strong reduction of the noise when there was a stop of fishing in August. So we are just wondering if it's better, what is better to use when we use, in this case, this you know, the time series for each station, in this case, just the data more than the maps.
Yeah, I would recommend to look at probably the 10th and 25th percentile at first, and see if you will probably clearly see the difference if there is a reduction of noise. I'm sure at the 10th and 25th percentile you'll see some strong effect.
Okay, I have another question that we found in the also starting to analyzing the data of the Acqua Alta station. Antonio also made what you showed before, so a correlation with meteorological data like wave height and things like that. But he found a correlation just with one frequency. So if I remember correctly, 63 hertz. Is that what we expect to find?
So did you do the correlation with the noise you measured, or just one component of the noise, as I was, for example, the background noise?
No, with the noise we measured.
Okay, so with the total noise, it's yeah. You won't see if there is anthropogenic noise. It's going to ruin your correlation. You really need to extract the background noise from your measurements to do the correlation with environmental parameters. Otherwise, it doesn't work because.
And how do you do that with the measured data?
So yes, there is a paper actually. We have published that, so you can probably start from this. So what you really need is to extract this signal here. There is a paper that we have published in the framework of the bias project. In the JASA Express letter, I can find you the reference and send it to you.
Okay, thank you.
Yeah.
Okay, Chris Predrag, I have a comment on that. I think it's very important issue. Also in the light of recommendations for a threshold value that we are working on in TG noise. So the modeling is a very important tool, and modeling is recommended as a tool for assessing reference level and impact level, but it is all more general. So the practical question will be when we model, what metric, what percentile we will use for assessing such levels, like reference level, impact level, and all that will be done in the future for assessing the impact of a noise. So this is important, you know.
Yes, it's very important and not an easy question.
Yes, because if I want to hide something, I will use one percentile. If I want to stress something, I will use another percentile. So I can play, yes, and I can make my reference level very high and say, okay, the all species or habitats are naturally living in a such high levels, and we have nothing to worry. On the other hand, I can say I can make the reference level very low and said everything is endangered. You know, it is very important, and that was my. This is beyond this discussion, but that was my comment on that recommendations and that methodology of thresholds. But so it is very important, you know.
Yes, the idea I've been pushing is that the percentile you're going to use should be related to, I mean, the threshold should define a percentile, meaning that it should come from the species you are interested in. If you are, and the effect you are trying to monitor and to control. If, for example, you consider that it's okay for fish to be exposed to 145 decibels 20% of the time, I think this is how the threshold should be formulated. If you think, if biology says, okay, that should be okay for them to limit the impact, then you would use the 20th percentile and look at the 145 decibel values on your map. So I think the threshold should define the percentile.
Sorry, Thomas. Yes. There is hello. By the way, there is some reference about these thresholds. I've seen you mentioned this PTS and TTS thresholds, but then you also just mentioned these behavioral thresholds, and I was wondering if there is some references about that.
Yes, I think it is Southall 2007 that already introduced. So they really introduced the PTS and TTS. How can I say? Kind of recommended values to use for impact assessment. And this reference, Southall 2007, has been updated and already 2 or 3 times, I think. Now we are more in a reference that is called NOAA, from NOAA 2018, if I'm correct. This is the very latest version. And already in Southall 2007, they were kind of suggesting that behavioral changes would start to occur, if I'm correct, at 140 decibels. So
but are you speaking about fish now?
I'm talking in general. We need to look more carefully, but I think it was more for marine mammals.
Mammals, yeah.
Yes. It's not solid. It's not very solid still. This behavioral level where you start to have some changes. It's not very clear yet, but we have there are some people working on it to have some better values.
Yeah, that was the reason for the question. I was quite curious. It was not a trick. It was a serious question. If there are any available setting right now.
I work on a project in Germany where the regulator said 140 level is one indicator and 144 decibels is a second indicator.
Okay, thank you so much.
So, you know, it's probably around that values.
Perfect, thank you.
Thomas, just a question. Maybe you can, if you can, with time, whenever you time, share with me the references, and then I will share them on the Basecamp with the for all interested people.
Yes, no problem.
Thank you.
I add this to my list. I started a list. Yeah, sure. Okay, looks like you're still alive, which is good. So now we're going to talk about percentiles all the time. So if you have some other questions about percentile, it's really time to ask them. All right. Okay, I'll go forward. All right, calibration of noise maps. And that's going to be the last item, I think, for this morning. Let's go. It's going to be quite technical here. Just a little bit of history here. We started this work in the framework of the Aqua project with a strong collaboration with UPC and the lab in Barcelona, because they were operating a hydrophone offshore Barcelona continuously, permanently. It's a cabled hydrophone. So the data was available continuously on that at a fixed position for 1 year. Well, we used 1 year of data, but actually it was running for many years. It's still running actually, and so that was quite a very ideal case for us to start to work on how can we use the measured data to calibrate our maps. And here I'm going to describe a little bit this work done in the project Aqua on this topic. So, as I said, we have two types of representations. You can look at your data as a time series. Here on the left, you have a received level as a function of time. Okay, this is exactly what is produced now with your algorithms that is processing the data. Good. Now, here on the right, this is a percentile view, a statistical view of this data set. Okay, so you have the received level here on the bottom, and you have the percentile from 0 to 100% on the y-axis. And it gives you a map like this, where you have, for a small percentile, like 10% percentile, you have higher levels than at a larger percentile. Okay, so the curve is always looking like this. We call that internally at QuietOcean, we call that an S curve, although it's not really a S, but doesn't matter. All right. Yes, slides will be available for internal use of the project. All right. So when you calculate all percentile, basically the way to construct this curve here is you calculate all percentiles from 0 to 100, and you report here the value of the in decibels you have obtained. Okay, or the other way around, you just take all the values from the minimum to the maximum of the values you have measured, and you calculate the amount of time you exceed that value, and that gives you the percentile, and it gives you this curve. And what we did is that we took the data provided by UPC and the lab, and the one we modeled at the same position of the hydrophone. All right, and it was quite intensive. We did one prediction. We did high resolution in time, so we did one prediction every 3 to 5 minutes. Okay, to have something very deterministic. And we superpose both of them. So here in what I'm going to present, the measure is always in blue, and the forecast or the modeling is always in green. And you can see that we have a fair superposition of both values. And when you look at the statistics, it's not too bad. We were able, for that period of time, we were able to reconstruct the statistics of what was happening. Okay, so that's all good news. So we did that in March, as I just showed. Okay. Then we did that in April, with still very good results. Then we did that in May. Then it started to drift. We started to have here strong differences between what we measured and what we modeled. And then we did the same in June. All right, here we started to drift very, very much. Okay, so we were not able to describe the statistics of the measured sound at that location. So we had to understand why, and that's the basis of then the calibration process we have developed. So what is happening here? Actually, it's the oceanography that is what is changing during time. The hydrophone is not moving, so it's not the hydrophone. The bathymetry is not changing, so nothing is changing but the oceanography. Okay, and if you look at the oceanography here, which is this middle graph here, middle image, depth versus time from March to end of July, and this is a sound speed versus so depth and time. You can see that in winter, in March, we were in a very homogeneous situation until April. And end of April, beginning of May, we started to have the sun hitting the surface of the ocean and changing the sound speed level, the sound speed at the upper layer of the ocean, okay? And more as the summer comes in, okay? And that changed the propagation very much. But the thing is that, well, but we were using this data of the sound speed. We were using it to do our prediction. Okay, so it's not a direct effect of that, but it's the only thing that changed. So it must be linked to this. We take that into account. So the sound speed profile was taken into account to our prediction here in green. So what is happening is that because of the thermocline here, the propagation of the sound is changing, and the influence and the sound is now, because of that thermocline, the interaction with the bottom is more important in summer than in winter, because in winter it's isovelocity. It's so the sound goes fairly straight, where in that situation in summer the sound is curved toward the bottom. So you have much more reflections on the bottom. The sound is reflected much more by the bottom than in winter. Okay, so the thing is that our description of, so it means that if my description of the bottom is not good, is not accurate, because it was sufficiently accurate in winter with small interaction between the bottom and the propagation. But when the interaction increased, this uncertainty on the bottom, or the error we had on the bottom, was amplified by the oceanography. Okay, and we started to drift. So then we said, okay, let's see if we can find a better bottom. And that's our first attempt to calibrate or ground truth the noise map, was to say, okay, I know I have uncertainties, and the main uncertainty, at least in the calibration process, is going to be the bottom type, the bottom geoacoustic properties. Okay, so I will use the measured data now to to reduce the uncertainty on my bottom properties. Okay, so I will basically, in my model, I will tell to the model that I have an a priori value for to describe my bottom, which is usually coming from, for example, from EMODNet, is providing an assessment of what is the bottom type. So this is an a priori knowledge we will use as the first approach. But if I have measurement, I will allow my bottom property, I know I have uncertainty, so I will allow in the model my bottom properties to change a little bit to have a better match with my measurement. Okay. So we have developed that thing and applied it to our data set in the project in Barcelona. And you can see that by changing the bottom properties, it hasn't changed much the results in March. It changed a little bit in April, but the good thing is that we were able to correct our prediction because now the bottom is better described, and the combination with the oceanography, it now gives us a good statistical representation and consistent representation of what has been measured. Okay, so here a synthesis over 5 months from the 5 months here. If we look at the overall statistical curve here, predicted without calibration, and it gives us the green one. One here is in blue. And when we do the calibration, when we correct the bottom based on the measurement, we are able to measure the total field as here in purple. And then, of course, it's not perfect. We've never reached zero here, a perfect agreement, because there are still other uncertainties in the marine environment, like the sound speed profile. We may have there are some uncertainties in the description of the temperature and salinity, of course. There are uncertainties in the source levels of the vessels. We don't necessarily have all the vessels described in the AES or the VMS data. So there is a remaining error, okay? And once we produce the calibrated map, we are able to evaluate at the end what is the difference between what I have measured and what the best I can predict. And this is here what we obtained for the period here, March to July. So we have 2 indicators of quality of the calibration. The one is how good are we to describe the anthropic component of the map. For that, we look at the higher percentiles. Actually, we look at this part of the curve. How far are the results? Actually, we look at the 10 to 25%. We don't go at the very, very low percentile because this is very rare, so it's not necessarily very representative. So we look at this region here. How far are we? What is the difference between both curves? And report the value here. And we can see that we have from a few decibels to 10 decibels remaining error. If we look at the average here, it's about 3 dB difference. And on the natural sound, so here we look at the percentile that are more representative to natural sound. So we selected 50 to 70% percentiles. So this upper curve here, where we have an error that is lower, below 5 decibels, more or less. That's what we obtained. And if you average, you are at 1.5 decibels. Okay. So we did that for at the regional scale. And in the bias project, we applied it. And the calibration was done. And here is one example of something that worked very well. Because we had a very, very, very good agreement between the measurement and the prediction. Apart maybe for the very, very low percentiles, which are not necessarily very representative because that's very rare events. So we did that for all the measurement stations. I think there were 38 or 39 stations. Some numbers are missing somewhere. And here is our parameters, the compressional speed of the bottom that describes the bottom. It's the speed of the sound in the bottom in meter per second. This is the parameter we play with. We say we have some uncertainty. Okay, so, and this is how much we had to change the compressional speed to reach the best calibration we could. And you can see that in some places we had to change the speed of the sound in the bottom by 80 meter per second. So it's typically the compressional speed in the bottom is about 1,600 to up to 1,900 or 2,000 meter per second. Okay, so we started from the a priori value given by EMODNet, and we have added to that value almost 80 dB here on the first station to get the match between the measurement and the modeling. Okay, at that was 125 hertz, and we have the results for the other frequencies here in color. Okay, so it's sometimes we need to add a correction, and sometimes not, because right away the data match the prediction. It means that the environment, the description of the environment was fairly good right away. We also used the BIAS project to refine a little bit that calibration procedures by detecting the passages of the vessels. Oh, I will go back a little bit. So we basically use, sorry, okay. We use here these small events, these rapid events where the vessel is passing by the hydrophone quite closely. And we use that values here to assess what is the source level of that particular vessel. Okay. This is to reduce the uncertainty we have on the source level. So it doesn't solve everything, because for the vessel that pass far away, but do contribute to the sound, that do contribute to the sound field, it doesn't work. But for the vessel that pass by very closely, it improves actually the calibration mechanisms. And you can see that on average here, from the a priori model we use to model the sound from the vessels, which is a random model based on the type of the vessel, the length of the vessel, and the speed of the vessel. We have updated that model because we know that there is some uncertainty in that model. So we had to change, for example, on average at 125 hertz on the first rig, we have added on average 8 decibels to our model to describe the vessels that were passing by this rig. And by adding this 8 decibels, we had a good match with the measurement. Okay, and again, it can be very variable according to frequency and according to the position of the measurement. Okay, so we have in the calibration process today, we have 2 degrees of freedom. The bottom compressional speed and the vessel source level. The bottom compressional speed is also is a local calibration, because obviously it's valid only for the on a circle, let's say, around the hydrophone, where well, in the detection range of the hydrophone somehow, where the source level is much more. We don't have all the vessels, of course, because the vessel needs to pass by the hydrophone. But once we know that, we can inject that that value along the entire trajectory of the vessel, even though the vessel is located very far from the hydrophone. So that's why it has more regional impact. And the indicator is the residual error, as I was mentioning, and this is in the BIAS project for the 40 stations, the residual error we had at the end of the calibration. again, on the anthropogenic component of the sound, the 10th percentile. And we have here, in some places, we have very good agreement, less than 3 dB, maybe less than 2 dB. In some places, it's a disaster. We have a residual error of 10 to 15 decibels. And that's probably because there might be something in the environment or in the human activities that we don't know. So maybe fishing activities that are not either in the AES nor in the VMS data or whatever, or maybe a wind farm, or maybe there was a construction around that was not described in the AES data because we were focusing on the shipping. Okay, there are many reasons for that remaining error. And on the natural sound component, we have something more regular. In most of the cases, we are around 3 dB uncertainty. And in some places, we reach, 6 or 7 dB. Okay, this is the same plot. Voila. This was for the calibration. If you have any question. I'm sure you have.
I have a question.
Yeah.
Okay, can you go back to the wave noise? Practically, when you estimate the noise produced by waves.
Is it that one? No.
Oh no, go back again.
Even before, all right.
Yes. When you
no,
when you estimate the noise produced by waves of a certain height, so you was working in the Baltic Sea.
Yes.
But this model is depending from the site or not? Because I think the noise will be different if I estimate waves in Adriatic or in Baltic Sea.
Yes, it's going to be different. You have a local effect because of the coastline, because of the topography, if you're close to the coast, because of there are many different, because of the structure of the waves that has a very local component. So it's changing from place to place.
So the best should be to have also for each hydrophone position, temperature, salinity, and a measure of wave height.
Yes, or of wind. Now we switch from waves to wind, so now wind is more appropriate. That's why we ask you to send us wind, if I'm correct.
Yes, but I produced wind by models, but I was thinking maybe in at least one station we should have measurements of wave height or at least wind. Not by
why
model,
not?
but measured by instruments. So probably it could be nice to see if there are some difference.
Yes. In bias we used the modeled wave height, and it was quite good, as you can see here.
Yes, I think that our wind model is good, but I'm not sure around all the Adriatic, North Adriatic Sea, but we can think to at least to estimate the uncertain on this aspect. And another question was just a moment, because I wrote. Okay, when you do the calibration, you change practically the bottom characteristics.
Yes.
Okay.
Exactly. Yes. Well, we changed the geoacoustic parameter because usually the information the data we have is I mean, the description is I think in English it's called Folegot description. It means it's sand, muddy sand, sandy mud. Okay, so what's the difference between sandy mud and muddy sand is quite difficult. although I have a small idea, but gravel, mud, okay, silt, okay, this kind of description. And of course, this is very fuzzy. So for each type of, for sand, for example, we have a range of validity for the acoustic parameters of sand. We know sand goes from more or less 1,650 or 1,700 to 1,850. Okay, so this is a range of validity we have for sand. Okay, knowing that the muddy sand is more towards the 160-50 meters, and the sandy or the gravel or the coarse sand is more toward the 1,800. So that gives us the validity and how we can play with the geoacoustic value.
Yeah, but if you calibrate the model, so for hypothesis, we suppose temperature, salinity, oceanographic data are perfect, and you calibrate the model modifying the acoustical properties of the bottom, in particular the grain size and the density of the bottom.
Yes.
At the end, you can produce a sort of, let me say, map of acoustic properties of the bottom.
Exactly.
At least,
yes.
At least for the points where you have the measure.
Exactly. At the end, we have an updated map of the bottom.
Okay. It was really interesting aspect for me.
At least around the measurement stations, okay? Where I do not have measurement, I don't. So what we do is that actually, yes, we start from the, let's say, the IMODNET map. And at the end of the calibration, we have a modified IMODNET map.
Yes. It's very interesting.
It's interesting because it's a way forward for, I mean, if, and we are thinking about, well, one of the questions we are thinking about is, what is best? Is it to have a fixed location for a very long period of time? Or is it best to have either a moving hydrophone or to have midterm hydrophones that do change. So let's say 1 month of measurement and or 3 months of measurements, and then you change the location. And we think that actually it's probably better the first or the second. I mean, the drifting or the moving platform is probably much better for the calibration, or maybe already to move the position every 3 months is probably an interesting strategy for calibration, for calibrating the maps.
Well, the best should be to have both.
Maybe both, but then you need to be richer.
Yeah. No, but it would be interesting also to move.
Yes, with the same amount of equipment, let's say, what is the best sampling strategy, you know, at the end? It's not clear yet in our head, but this is something we think about.
Okay. Okay, thank you.
I think there was another question.
Yes, please. Hi, Thomas.
Hi.
I was asking about waves. Maybe it's more important to define if you have a breaking wave condition in terms of impact on sound pressure, isn't it?
Yes, it's true. You have a different regime actually, and maybe it's not very clear in that data set. Actually, here we decided to have a simple model, which is a logarithmic law. But actually you have, for example, here in the when the wave are not very significant, okay, so the ocean starts to move, the noise do not pick up immediately. Okay, you need to have a certain value a certain significant wave height, to reach a certain wave height before the background noise starts to pick up. Okay, so actually here it's not here. This is not correct. Actually, what we do now is to have a plateau for the first at the start of the curve. Okay, so it's a constant value, and then it starts to pick up. Here, in that case, it would be after, let's say, almost a meter or 80 centimeters. We would use maybe 70 decibels or 69 decibels, and then we will follow this curve. And you probably have the same thing when you change the regime of waves. I'm convinced of that, because the more bubbles you have, because here at the start, as you say, you have less bubbles, and then the bubble starts. So you may have it might be more complicated than what we did with different regime with the C state.
But it depends on the sea level and so on, the condition and wavelength. And maybe I was thinking that maybe in our site we have some video recording, so maybe we can check if reaching some sea condition with breaking wave, if you observe something in our recordings.
Oh yeah, that would be very interesting to have a look at that and to see how it changed. Yeah, when we start to have white caps and when you don't, and and from the direction of the waves, maybe that play a role. I don't know. The combination between the swell and the wave from the wind, you know. Sometimes they are in the same direction, sometimes they're crossed. Here you have, I think you can study that for the next 10 years. Yeah.
Maybe we can look at Fantina for the very last one, last storm we had here. So maybe I can save some recording from the last day, so to check if there's some impact on the noise recording.
Yeah, that would be great. I think Antonio saw something, but now when Thomas will send us this publication, we'll try also to separate better the geophony, so to say, and then we can see. Yeah, maybe we can also try to do this check. Yes, with the video. That would be nice. Thank you.
Thank you.
Yeah, and so this we have just to continue your first question, Fantina, on the correlation. We have a correlation here. We calculate that correlation for each frequency band, and we have a different value. I mean, it changed when you change the frequency. It changed a little bit this model, this correlation, and it may not be. You may not have correlation for all the frequencies, because the wind noise is more in the lower frequency, so from tenths of hertz, and maybe 100 hertz to 1 kilohertz, maybe 2 kilohertz. Okay, so above that, you may not see any correlation.
Okay. Yes. Okay.
Okay, so it's good to do that band per band. If you do broadband,
that's what Antonio did, in fact. But
yes.
Okay. Thank you.
If you do broadband, you'll have the correlation will not be as good as at one band, because at some frequencies you don't have correlation, so it will degrade your correlation.
Yes. Mm-hmm. Okay. Yeah.
All right. Any other question?
Andrea had a question. If you can then share these slides with us afterwards.
Yes, I will. If you use it for internal use for the project, I can share it.
Okay, thank you.
Yeah. I will send it tonight when I'm done with the second session. if I can still talk after the next 2 hours. Okay.
Okay, if there are no more questions, I would suggest that we meet again at 2. I will leave on the meeting. I will stop recording, of course, and so there will be two recordings parts. I will just leave on the connection, but you can disconnect, and maybe someone can stay. So Mauro, maybe you can stay connected, or Antonio, I don't know, so that we don't lose the connection. But for the others, we can meet again at 2. Okay.
Yes, very good.
Okay, thanks a lot, Thomas,
Yes.
for the very nice presentation, and we hear you later on.
Yes. Okay. Bye-bye.
Bye.
Bye.
Ciao, bye.
Ciao.